Hello and welcome back to Calculus 3. We are starting chapter 12 on functions of several variables. The first section is on planes and surfaces. So we have, so what would be the plane? The surface of the desk that is flat, like the floor or the ceiling on a wall. We already talked about the most basic cases. We know that the plane, the xy plane, is denoted with z equals to 0, and then our ceiling would be z equals to 10 because it's 10 feet high. And we know that we can describe each one of the walls using basic equations, either x equals, y equals, and then for floor and ceiling, z equals. But then the plane could be at any angle to the any one of these default, let's call them, planes. So what should I do about that? Well, let's go and first write the definition of a plane. And then we'll go from there. So definition of the plane in R3. P0 and a non-zero normal vector n, right? That's a normal vector n. The set of points P in R3, right, in 3D, for which is called a plane. So we cannot define a plane by saying, yeah, it's a flat surface. Right? The way we define a plane is we pick a point on a surface and we put a vector at that point. So now that point is point P0. And all other points here are points P, because the coordinates of the points P are x, y, and z. So they can take on any values. However, only the points P, which have coordinates such that the vector P0P that is in the plane, so only those points that give us the vector that is perpendicular, orthogonal, to the normal vector n, which is the black marker here, all of those vectors, right, all of those points would give us a plane. So all of those points that you can find, no matter how far they are, right, and they constitute a plane. So that's the way to describe this. Now, again, that's the definition. And the way we work with this is I'll draw a plane, and then I will place the point P0, and I will pick the arbitrary point P, whose coordinates are x, y, z, while the coordinates of P0 are x0, y0, and z0, and what's important about that point is the fixed point. Right, so you have that one fixed point, P0, with values given. Now, we have the normal vector n, and there is a 90-degree angle between these two. Now, there is going to be another vector P right here with also having 90-degree angle. There's going to be another vector. I don't know if you can see this or not, but there's a yellow vector here, also 90 degrees, also P. So you can have a whole bunch of these vectors. So these x, y, z here are variables, right? And they take on every position on this plane. Every position on this plane. So now, if you look at the geometry of this, we'll define our vector n to have, let's say, a, b, c components to it. We know that our point P0 has x0, y0, z0 coordinates. I don't know equal there, just P0 has those coordinates. And we know that the point P has x, y, z coordinates. Those are variables. We can create a P0P vector. Creating a P0P vector is a simple subtraction of x minus x0, y minus y0, z minus z0. And we are requiring that this vector P0P, which is our black vector, blue vector, and yellow vector, requirement of that vector is to be orthogonal to the green vector n. What mathematical concept we can write for orthogonal vectors? Dot product is 0. Very good. So I'm going to say that the dot product between the vector n and the vector P0P needs to be 0 because vector n is orthogonal to P0P, right? That's the explanation why. So we get to write the dot product between these two. Well, if we have a dot product, then let's write out the dot product. That's ABC dotted with x minus x0, y minus y0, and z minus z0. That needs to be equal to 0. And from there, you actually get your equation for the plane. You have A times x minus x0 plus B times y minus y0 plus C z minus z0 equal to 0. Now this is already equation for the plane. This is equation for the plane, and now what I do is I distribute A, B, and C and combine all of the constants into a single constant which I'm going to call D. So I have, when I distribute, so this is the alternate form now. I have AX minus AX0 plus BY minus BY0 plus CZ minus CZ0 equals to 0. I leave AX plus BY plus CZ. I leave that on the left because those are the variable terms. On the right-hand side, I have AX0 plus BY0 plus CZ0. And this is a constant. And we usually call it D. So now the alternate equation for the plane is AX plus BY plus CZ is equal to D. And that would be, you also have the definition for your D right here. That's the definition for what D is. D is all these constants combined. So these are the two forms. So plane in R3, right, in 3D. This is also plane in R3. You can use, I mean, you will be using each one of these. So now, I hope you remember from your previous mathematical experiences when you were solving a system of 3 equations with 3 unknowns, right? Well, if you just consider one of those equations, let's say it was 3x plus 4y minus z equals to 9. That's equation for a plane. So now as you are upgrading your mathematical knowledge, I guess, or whatever, think about it. When you have equations of 2 equations and 2 unknowns, a system of equations for 2 variables, you have, let's say, x plus 3y equals to 6 and x minus 2y equals to 5. What you have here are 2 linear lines. And by solving the system, you are looking for the intersection of those 2 lines, which is xy, which is when you solve the system, that's what you get. X equals a number, y equals a number. If the lines are parallel, they don't intersect, and then there is no solution because the lines do not intersect, they do not create common xy that works for both equations. And the third case is when the lines are the same, they graph on top of each other, so you have infinitely many solutions. Now, when you go to the 3D environment, you will have 3 variables and you will have 3 equations. What you are doing in that case is you are intersecting 3 planes looking for a point of intersection x, y, z. That's the corner of your classroom. This classroom has 8 corners. There's a corner in the top over there and a corner on the bottom. That's 2. And then another 2 and another 2 and another 2. 8 corners. These planes, ceiling, floor, walls, they intersect at those coordinates. So when you are solving a system of 3 equations with 3 unknowns, what you are effectively doing is you are looking for the point, the coordinates of the point where those 3 planes intersect. So now some of the mechanics of what we are learning you already know. If I am asking on the exam or homework or whatever, find the intersection of these 3 planes, well, the planes could intersect at the planes could intersect at a single point. They can also intersect in the single line. The planes could be parallel because the floor and the ceiling do not intersect anywhere. So there will be no solution to that system, right? And you say, well, hold on, it's just a ceiling and a floor. Yeah, there's another floor under this floor, right? So you actually have 3 planes and they're all parallel to each other. There's no solution because they don't intersect. I can intersect 3 planes together. So it's going to be difficult to. So think of this kind of intersection here, right? So if I intersect these 2 planes together, right? I have a horizontal and vertical plane, and just through the middle, I intersect these, and then I can make that. I could have ripped the homework over there because it's not picked up anyway. Whatever you don't pick up, I'm going to burn in some kind of ritual anyway, so. You go figure it out. All right, so. All right, so here we go. I should have done another one because I can't rip this to half. Thinking. Anyway. So I can intersect 2 planes. Obviously, there's more. And this as well. Used to carry sword with me, and then the VP said I can't do that, so. Now I have to read paper like a peasant. Actually, no, even a peasant do this somewhere. Anyway, here, two planes intersect, and they create the shape, and these planes intersect at a line, right? Now, if I create one more of these, right, cut it halfway through, I can slide that one as well, and then and put it at this angle here, and then you would have three planes intersecting at the line. I don't have to have three planes intersecting in a point. I do have it over there, so it's easy to see a ceiling wall and a wall, and there's a point in the corner, right, which coordinates we can find. But in this particular case, I can slide another plane at this angle here, and you would have this line of intersection here to be intersection for all three planes. So you can have all of these combinations. And the way to solve that, to find either a point or a line, is a simple three equations, three unknowns, and go. Right? So equation of the plane is something that you have seen before. It was not defined as equation of the plane, but if you have worked with it. So now, if I want to think about whether the planes intersect or not, all I need to do is to solve the system of equations. So, to find any kind of intersection of two or more planes, solve the system. That's that. So if you get that x, y, and z is equal to 1, 3, and 5, then they intersect at the point. If you get that you can't solve for plus z is equal to 1, right? You have these two planes given. So this is going to be a plane number 1, so P1, and plane number 2, P2. You have two equations given. Simply by solving the system, you will see. Now you immediately see, okay, I'm intersecting two planes. They can't intersect at a point. I need a third plane at least, right? But these two planes are either going to be parallel or they're going to intersect at the line. Over there, that edge, I showed you the way in which you could have the line be intersection, but you know. So now, if we are to solve this, we can add equations, and that's going to kill z. So I have 2x plus 3y is equal to 4. That thing is a line. You can go and you can massage it into y equal mx plus b form if you want to, but this is the equation of a line. So these two planes intersect into a line. And that line can be graphed, and there you go. Now, angle between two planes. To find the angle between two planes, what would you do? How would you find the angle between two planes? So what would you do to find angle between two planes? You have two planes intersecting. It's a terrible drawing. All right, so these two angle between these two, angle theta. Very good. Each plane is described by its normal vector. So if I'm intersecting two planes, each one of those two planes would have normal vectors, and the angle between those normal vectors is the same as the angle between the two planes. Excellent. So the plane P1 will have the normal vector N1, and the plane P2 will have the normal vector N2. So the theta, which is the angle between the two planes, will be the inverse cosine of N1 dot N2 divided by the magnitudes of N1 dot N2 on times, same thing. So the angle between two planes can be found by simply figuring out the angle between the two normal vectors. Nice. Let's do some algebra. Find the equation of the plane going through points 0, 1, negative 2, 1, 2, 3, and I don't know, negative 1, 2, and 6, whatever. So find the equation of the plane going through these 3 points. First off, let's talk about the concept. Guys, if you're describing a line in space has to have 2 points to be defined. Here's the point number 1, point number 2, and if you put the line on through those 2 points, this line can't move anywhere because it's anchored, right? So if you need to stretch a cord, you have to connect it to the 2 locations, right? You connect one side, and then you stretch the cord between the 2, right? So you have to have 2 points to define a line. If you only have 1 point, right, then the line can wobble on that 1 point in any way, so it's not defined. It cannot be defined by 1 point. In calculus, you might say, well, wait, hold on, a tangent line is at 1 point. Yeah, but you also have a function, and the function, which derivative gives you the slope, determines the way which goes. So sure, if I have a point and a direction, which is again 2 pieces of information, I can set the line with 1 point, but I have to have something else, not just 1 point. Now, for a plane, if I have only 2 points for a plane and I rest the plane on it, you'll see that plane wobbles, right? The minimum amount is 3 points, because at the 3 points, plane is perfectly stable, so the 3 points is the least amount of, right? So you will find some of those funny cars, right, with three wheels, right? You will find the coffee tables with 3 legs and chairs with 3 legs, and so on. Why would I make bar stools with 3, right, rather than 4? Because it raises a lot more funny situations, right, when a bar stool has 3 legs. Yeah, so that's that. So now, how would you find the equation of the plane having 3 points? First off, you ask yourself, what is that you need for the equation of the plane? Now, what did when we did the derivation, what were the 2 things we had to have in order for us to do the dot product and all of that stuff? We had to have 2 vectors, good. So what are my vectors now? Good. So we have to first pick which is going to be our fixed point. And you have to stick with that throughout the problem. So you have one of the 3. Which one do you want to be your fixed point? Obviously, you want the first one because that's the go-to one. Okay, fine. So that is your P0 immediately, which makes this into your point P. Great. What can you create if you have P0 and P? Good, you can create two vectors. So now you have two vectors that are in a plane. How are you going to get out of those two vectors in a plane the equation of the plane? Cross product of the two vectors in a plane will give you the normal vector, right? The equation of the plane requires you to know normal vector because that's your A, B, and C, that it's on the left-hand side. So your job is to find the normal vector. Great. You do the pairs, you will get two vectors, so you can call it P0P, P0R, or whatever. So you will find two vectors, and then those two vectors, you have to do the cross product to come up with the normal vector, and there is your equation of the plane. All right, let's get busy. We're not getting any younger. Okay, so let's see. I'm going to call these points, let's say P and, how about R and Q? So I have P0R. I don't know why I'm doing this red. So P0R vector is going to be 1, 1, 5, and then P0Q vector is going to be -1, 1, 8. The normal vector n will be the cross product between P0R and P0Q. So the normal vector n, we have 1, 1, 5 cross with -1, 1, 8. And that cross product is 8 minus 5, that will be 3. And then we have 1 minus, no, sorry, 8 plus 5, so it's -13. And then we have the last one over there, that will be 1 plus 1, 2. Is this what you guys have? All right, good. So now we have that product, and now we're using the fixed point, the P0, and we're using this one. So we have 3x equals to 0. Now this is already done, right? This is the first form of the line, but we can do better. Oh, of the plane, sorry. We can do better, so that's 3x minus 13y plus 13 plus 2z plus 4 equals to 0. Move all of the constants on the other side. So 3x minus 13y plus 2z is equal to -17. And that's the equation of the plane that goes through those 3 points. You can practice this easily by picking any 3 points in space and then computing this the same way.
You get the same answer if you change it.
Yes, but you have to get the same answer if you change. But see, the trick is that you have to also be careful if you change the fixed point, right? You have to be careful which way you subtract values. Okay, so the fixed point is the P0 point. So when I go back to our derivation, when I choose a fixed point, then all other points are the other point minus the fixed point. So that's the first thing. And also, when you are making the equation at the end, fixed point has to go for x0, y0, z0. Right? So there are, you can use any combination you want, but you have to be very careful which way you are subtracting. Also, it's important with a cross product, right? With a cross product, well, if you go first vector times the second vector will give you the normal vector on one side of the plane. If you reverse the order of the cross product will give you the other side of the plane. Now, that's not an issue, right? We know that it's not commutative. That's not an issue because the difference in a cross product is the negative sign. Now, in the dot product, whether it's positive or negative on n, it doesn't matter because it's equal to 0. You can multiply both sides by -1 and nothing is going to change, right? So it really doesn't matter. The cross product, it doesn't matter which way you do, whether it's the first times the second or second times first vector, because it's later that n is dotted into a 0, so that doesn't matter. But it matters to actually obtain all of the other vectors. That's what matters. Great. Parallel and orthogonal, right? We talked about it. So dot product and the cross product. You can do that for angles. Parallel planes, intersecting planes, we all did that. And okay, good. The next part of this lecture is on cylinders and traces. So, definition. Given a curve C, in a plane P, and the line L not in P, a cylinder is the surface consisting of all lines parallel to L that pass through C. So I am aware that when someone says cylinder, the only thing you think about is a pipe or your let me see who has the. Yes, that's a good example, because I'm looking for these that don't have curves, right? So that's a good example of a cylinder. Also, this bottle, if you cut up the top portion and just look at this, right? That would be a cylinder, or a regular soda can, right? I can't use yours because yours has the. I mean, we can cut it off, right? But so you're familiar with that, but that's only one of the special cases, because your curve C for object like this is a circle, right? And then you have the axis in the middle, which is acting as the line L from this definition. And if you have a circle C, every line that passes through C and it's parallel to the line L, which is the axis in the middle, constitutes a cylinder. So sure, the cylinder that you all know and love is a cylinder, but it's a special case. The textbook shows the image of a homework paper bent as a parabola, where you have a random line. So you have you draw parabola on a desk, and you fit the paper so that it follows that parabola on a desk. It's a cylinder, because it fits the definition. It's not a special case of the cylinder that we are all used to, but it is a cylinder. So cylinder is anything that is going to follow those rules. So you are going to set a curve on a surface. You're going to put one line through that. It doesn't have to be in C, but it could be. And then any other line that is parallel to that line L, all of those lines would create this shape, and that shape would be called a cylinder. Actually, wait, I can show you the image from the textbook. So these are the examples. So you see up there like a skateboarding ramp or whatever, right? that is a cylinder, because you have in that case YZ plane contains the line C, and then you put one line L through that line C, and all other lines that are parallel to it that go through C would create the right. You can play with these kind of shapes with those. I don't know what they're called. For the beach, they made out of like a straw thing, right? You can't use the towel because towel really goes everywhere, right? But if you use the thing for the beach, that's really good thing to play with, to see these outside of the images there. Paper also is kind of wobbly and goes all over the place. And then each one of those straws, I hope you know, that, what are they called? It's for the beach. It's made out of straw, and it looks like a towel, but it's not a towel. You are doing this. So what's the name?
I don't know.
Is it a mat? A straw mat?
Yeah.
Straw mat? Okay. I have no clue. Yeah, there they are. This thing. See, you can buy it for $4 right there, and then in a comment, with a special, when you order something and they say any special instructions, right, you just say, thank you, I need this for my Calculus 3 class, right, to understand the concept. I hope you're not going to the beach, it's outside. Yeah. We spend tens of thousands of dollars, hundreds of thousands of dollars to perfect the inside, right? It's nice and enclosed and air conditioned. And then someone says, I'm an outdoors person. You're savage. Outdoors. That time is over, okay? When we had to live outside and run to the cave, right? No. We have inside, we have the computers and TVs and fridge and air conditioning. Why go outside? If they figure out the indoors beach, like I'm in, not the pool, I mean, it's a bowl of water, everyone is, no. If anyone goes and puts like a concrete building around the beach, or like, let's say, I don't know, half a mile over the water, yeah, I'll be there. First one there. There's your entrepreneurial idea. Why are you still sitting in this class? There's the market right there. There are people like me. You can go to the beach in any weather. Doesn't matter, right? It's indoors. No? Not a good idea? You'd rather stay sunburned with whatever those skin cancers are called? All right, fine. Be my guess. I'll stay indoors, play video games, happy and healthy. Great. So that will be a cylinder. And then we are going to talk about the trace. So another definition. A trace of a surface is the set of points at which the surface intersects a plane that is parallel to one of the coordinates planes. I'll just shorten this and say names, XY trace, XZ trace, and YZ trace. So those are the names. What is this? This is, you have a watermelon on the table, take the sword, you take the sword, and you go, yeah, right? What happens? You make a vertical cut on the watermelon. What is a trace? A trace is on the outside of the watermelon that, the edge that it shows, in which case would be ellipse. So that cut you can call, let's say, YZ cut. Then you can have, so if this is a YZ cut, then this would be XZ cut, right? Perpendicular to it, XZ cut would also show an ellipse. And then you can also cut parallel to the table through the middle of the watermelon, let's say. You don't have to go through the middle, you can go anywhere, which would also trace an ellipse. Trace is a two-dimensional equation that you get when you cut a 3D surface with a plane. That's what you're getting. And now those cuts are parallel to one of the coordinate planes, which means that you're always cutting with the equations z equals 0, z equals 10, z equals 5, something like that. Or x equals 1, x equals 2, x equals 10. You will always be cutting with some of those. So now, if I take an arbitrary equation, let's take, this is not umbrella, but it's good enough. Let's say you have, we'll talk about these equations, but I want us to go and say z equals, let's say 9 minus x squared minus 3y squared. This is going to trace elliptical paraboloid. So you are going to actually have something that looks like an umbrella. But it's going to be elliptical. It's not circular. Umbrella is a circle, right? Now you take umbrella and you squish it on two sides a little bit, right? And you create, well, there's your another idea for entrepreneurship. You create the elliptical umbrella. Elliptical umbrella is great for two, right? Now you make it a little bit shorter on the front and the back and a little bit wider on the sides. You can put two people under it. Like because every time you're with someone under the umbrella, your shoulder is wet, right? Which is the reason why we never invite anyone under our umbrellas, right? Because it's better for them to be all wet than for our shoulder to be wet and the other side dry. It's uneven, right? It's not good. So, or get your own damn umbrella, right? It's like $5. So, I know, terrible, right? You are only 2 feet away from needing the umbrella, actually. They gotta fix that thing. Anyway, so, wow, this is like idea number 2 for you to make. So what do we have? We have the indoors beach, right? So we need to create a huge structure over the beach, so it's nice and air conditioned and enclosed, and it's not exposed to the sun and cancer and everything else. And then also now elliptical umbrella for 2. Good, right? Now what happens here? See, this particular elliptical paraboloid is going to have its height at 9 because, trust me, I know why. And what's going to happen here is I'm going to cut this shape, so cut shape with z equals 5. Z equals 5 is a plane cut through 5. That thing better trace an ellipse on the edge of the cut. So we should be able to detect that through our calculation by substituting z equals 5 in our original equation. So now we have 5 is equal to 9 minus x squared minus 3y squared. Put x and y squared on the left-hand side, move 5 to the other side, which creates 4. Divide through by 4 to get your 1 on the right-hand side. And there you go. Ellipse. Exactly what we were expecting. Exactly what we were expecting. If you cut away, right outside of the shape, you should get nonsense. If you cut with a shape z equals something more than 9, then you are going to get the equation to equal a negative number. We know that's not equation of the ellipse. Equation of the ellipse equals a positive number, right? So if you know your basic shapes, equations like circles and ellipse and stuff, this parabola, hyperbola, this stuff is going to be a joke. If you don't know equation for the ellipse and a circle and hyperbola, obviously this stuff is going to be tough because you don't know prerequisites. So when you get your 3D shape, which describes a watermelon or a horse saddle or umbrella upside down, or your cereal bowl, or a plate, whatever, there are equations. There are calculus 3 equations. There are surface equations, like that one. That's called a surface equation. That's in the title, surfaces, right? When you have an equation like that, you can cut that equation, and when you cut that equation, you get the shape that you actually see as a trace of the outside of that shape. No matter which way you cut the watermelon, you will get an ellipse. You have to. No matter which way you cut your basketball with a plane, you are going to get a circle because it's a ball, right? You circle this way, circle that way, circle this way, right? No matter which way you cut, it's always going to be a circle. What do you get if you cut this umbrella with either XZ or YZ cut? With any vertical cut. What do you get? Parabola. Now let me show you the magic of these cuts. Boom. Parabola. Y equals x squared, right? That's a parabola. So if you are cutting with a plane in the y direction, y equals 5, y equals 6, y equals 1, y equals -1, whatever, that eliminates y from this equation. What's left is a parabola. And that is your trace. If you cut with x equals something, there's another parabola. This parabola is in yz location. If you cut something with z, that dies. There's your either a circle or an ellipse. If these numbers are the same, it's a circle. If they're different, it's an ellipse. But it's a very simple thing if you know the shapes, right? And then obviously you take a look here and you say, all right, so I have a parabola, right, that cuts into it. It will be a parabola. Now the book, obviously, right, it's $200. They better have the picture for that. There it is. Now they're not using elliptical one; they're using one with a circle. But who cares? If I'm cutting with a z-plane, z-plane is in the xy plane. So xy trace, in this case, is a circle. Right? I had the umbrella. This is a cup, whatever. Here's your xy trace. It's a parabola, and there's another parabola there. This shape is called elliptical paraboloid. Why? Where's the list of the things? There, look at that. See that on some roofs of industrial complexes, and so they have the roofs like that, right? That's the simple sine function in one direction. All right, quadratic surfaces. There's your watermelon. This thing is called ellipsoid. ellipsoid because no matter which way you cut, you get an ellipse. And there are all the cuts in one spot. You have the green cut, the red cut, and the blue cut. Right? And they're all ellipses. Now you see that from the equation of the ellipsoid, because no matter which one you remove, whether you remove x or y or z, the remaining stuff is always an ellipse. It's really cool. Here's the same problem we did again. They really went out to explain this. There is the hyperboloid of one sheet. Right? These are hyperbolas. When you cut, they have ellipses or circles on the green cut, right? You see the Z cuts over here. And then you see the red and the blue cuts, right? We'll discuss that more in detail. There are cones, hyperboloid of two sheets. And, this is what I was looking for. Good. So it's page 869. On page 869, you have these basic quadratic shapes. We'll start with watermelon, all right? So we'll start with the watermelon, which is an elliptical shape in R3. These axes are terrible. Much better. So when you are dealing with this, I'm writing the same equation. You need to be looking at the nice picture. So the equation for this is given as x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. So now, all three traces for this particular shape are ellipses. If you remove x variable, you are left with y squared over b squared plus c squared over, that's an equation of ellipse, right? If you remove y variable by saying y is equal to 1, you want to cut at y equals to 1, you are going to get an ellipse again, because you will have x squared and the z squared. And if you remove z squared, right, you will get, again, x squared and y squared. So no matter which way you cut, you always get an ellipse. So this thing is called ellipsoid. A student asked me, do I have to memorize the name of this? Please don't. Like, use just, few digits of the IQ. You see the shape. So what it consists of? All ellipses? Ellipsoid, right? It's as simple as that. Look at the next shape. Elliptical paraboloid. Why? Well, that's the umbrella problem we did, right? If you cut with the horizontal planes, you get ellipses or circles. Circles are special ellipse cases, okay? So we just talk about ellipses. We don't have to mention circle ever. Because circle is just what a square is to a rectangle, that's what circle is to ellipse. A special case, right? Square has all sides the same, and a rectangle has two pairs. Well, ellipse has two different radii, right? The large one and the small one, major and minor. Circle has the same. Those two radii are the same length. So what square is to a rectangle, circle is to ellipse. So we never have to mention circle ever again. So why is it called elliptical paraboloid? Because if you cut with horizontal planes, you get these ellipses or circles. And if you cut them vertically in any way, you get paraboloids. So elliptical paraboloid. Anything that looks like a cup, whether it's upside down or whatever, it's going to be elliptical paraboloid. Now you also, when you look at the equation for elliptical paraboloid, you get that z equals to x squared over a squared plus y squared over b squared. If z is a number, you are getting your ellipses or circles. If you kill either x or a y, you get parabolas. So they're both included in the name, so we're all happy. Next two shapes are hyperbolas. So the next two shapes are hyperbolas. You have hyperbola of one sheet, hyperboloid of one sheet, and hyperboloid of two sheets. So hyperbola is a 2D shape which has either horizontal or vertical orientation. And hopefully when you compare that to the shapes that you have, you see that the 2D hyperbola, I draw the 2D hyperbola again, and then I just add the 3D feature to it, and I create a hyperboloid of one sheet. What's important is that you have the same hyperbola on the side over here. If you go to the second 2D hyperbola image and you add roundness to it, you create the second shape from the image, which is a hyperboloid of two sheets. So vertical and horizontal hyperbolas create two different shapes for your 3D quadratic surfaces. Their equations, right, that are listed to the left of the shape, still can be manipulated with trace by killing one of the variables and reducing those to the 2D equations, which are either hyperbolas or ellipses, i.e. circles. So we have x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 1. And you see that for the one sheet hyperbola, if you kill the x direction, you get hyperbola because you have minus, right? So if you kill x squared by saying x is equal to 1, you want to check what's happening at x equal 1 cut, or x equals 0, it just kills the term, doesn't matter. If you cut at 0, right, you get the hyperbola. If you kill y, you still get the hyperbola. And if you kill z, meaning you are cutting horizontally, well, you just kill the negative term, you are left with x squared plus y squared, that's either a circle or an ellipse. But these are, right, all circles when you cut them horizontally. So that all makes sense. On the other side, the bottom equation has the negative x squared over a squared and negative y squared over b squared plus z squared over c squared equals to 1. Same thing happens. If you kill x, you have one positive, one negative square, that's a hyperbola. If you kill y, you have one positive, one negative, so again it's a hyperbola. And if you kill z, well, this is negative and negative, move the negative to the other side, right? With the appropriate cut, you will be getting your ellipses or your circles. See, there is this negative space, right, in between. Those are the z values that you cannot use to cut the shape. So if you are anywhere in this realm here, your equations will not work out to find the trace, because obviously there is nothing to trace in that space, right? The circles and ellipses begin on these elevations, right? So lower and higher than those two elevations so there is a range of z's that you are allowed to pick. Where hyperboloid of one sheet, you can pick whatever hell you want. It will work all the time, right? Because this hyperbola is going to extend indefinitely to left and to the right, and the shape is going to go forever up and forever down. So you can pick any z, any x, any y to get your trace cuts for the one sheet, but over here you are not allowed to pick these values here because those values would not give you equations of circles and ellipses, because there is nothing on this level. Then we have an elliptical cone. That's technically the one that you guys haven't dealt with in this sense. You have extensive knowledge on linear lines and intersection of linear lines and slopes and all of these kind of things. And these are two linear lines intersected at the origin. And then you add the 3D aspect to it, like that. So the equation for something like this, right? X squared over a squared plus y squared over b squared is equal to z squared over c squared. Remember that we had the paraboloid, which looked like this. It was the same left-hand side, but it was equal to z instead of this mess. It's a very similar equation. So you have to be a little bit careful about that, not to confuse things. Now, what happens as I say z equals to some number? If I say z equals to some number, then this thing over here dies, and when that thing dies, you just get your circles and your ellipses, right? So that makes sense. But what happens if you kill either x or a y? Right? Doesn't matter which one. If you kill, let's say, x, you get y squared over b squared is equal to z squared over c squared. Everything is squared. So you can square root both sides. But you have to put plus minus when you square root both sides. And what you get is y over b is equal to plus minus z over c. Now I can rewrite this as z equals plus minus c over b y. That's a linear line through origin, right? Linear line through 0, 0. That's what it is. So those would be the linear lines, straight lines, and this creates the cone. So no matter if you kill x direction or the y direction, you get those two lines. And you get both plus and minus because algebra, right? You square root both sides, you better put plus and minus on both sides. I mean, on one side and then... Yes?
Isn't this basically like the same concept as conic sections from algebra 1 to algebra 2?
Mm-hmm. These are the conic, yes. We're just upgrading that a little bit into Calc 3. The last shape, what does it look like? Looks like a saddle. Looks like a horse saddle. And in my opinion, the most interesting shape of all shapes. All other shapes are somehow natural, and this one, right? I mean, obviously, unless you're into horseback riding and stuff like that, you don't deal with this shape on a regular basis. But this particular shape is very interesting because it has one thing that no other shape has. And I'm not sure if you can actually notice what that is. So, what would we call this point and this point here? Okay, or? Yes?
Maximum.
Yes, maximum and minimum. This is a maximum and this is a minimum. And they occur at two different locations, which makes sense, right? You can't have min and max at the same point, right? Wrong. You can. You see where the common sense immediately goes out the window? Because we start over here. That point is at z equals, I don't know, -2, and that's at z equals +2. So this is a max, this is a min. They're not at the same point. So you would never say that min and max can be at the same point, which is wrong, right? Bing. Look at that. We call that a saddle point. If you look at this point, right? Let me help you out over here. There's your horse. Stop laughing, I'll kick you out. This is a horse. Here. And the eye and the fangs. You know it's a horse. No question asked. Now, there's a saddle on which you are going to sit. If you look perpendicular at the horse, that point is a minimum. But if you look at the horse, it wraps around the horse, is a max. Same point is a min and a max at the same time. And we call that the saddle point, right? To saddle the argument between min and a max. So, yeah, haha. So, hyperbolic paraboloid is the only shape that you actually have to study, because it's nothing like the shapes you have dealt with before, and it has this weird feature that most likely you never even considered before, that min and max can be fused into a single point and call that point, right, something else as a saddle point. Remember how Calculus 1 had optimization where you were looking for min and max, right, when you set first derivative equal to 0? You remember how you had word problems to figure out maximum profit and all of these kind of things? All of that stuff is back in Calc 3. Sections 12.8 and 12.9 are going to be figuring out min and max, and now added saddle points, because we have more things to worry about. So these kind of things will now, start happening more often, right? Eventually you're going to have to run into an argument where negative infinity and positive infinity are the same thing at the same point. And you go, huh? Like, yes. And if you go really far in math, you learn how to actually fold the 3D space in a 4-dimensional space and put your north and south all at the same location. And you go, what? And I said, yeah, we can do that. It's called mathematical gymnastics. All right? So, the courses have names, but we can do all that stuff. So now with that knowledge, exam is tomorrow. Please complete today's quiz. You have one quiz tomorrow to warm up. I will see you all tomorrow for exam first. And then after that, there will be a 12.2 lecture after the exam. And then the weekend. Yes.